A very good morning to all of you. So, today we have come to the last section of electricity and magnetism, and that is electromagnetic waves. So, today what I will do is I will discuss about electromagnetic waves, what do they represent and what are these waves and what kind of frequencies, etc., etc. So, recall we have been discussing the basic equations which describe electricity and magnetism. So, let me write the 4 equations that we have obtained through the course on the lectures on electricity and magnetism, and these are called Maxwell's equations, because Maxwell added a term which I described last time as the displacement current, and that is a very important contribution that predicted the existence of waves which are now called electromagnetic waves. So, let me first write down the Maxwell's equations. So, first of these equations is integral E dot dA, charge enclosed by epsilon 0, integral B dot dA is equal to 0, integral E dot dL is equal to minus d by dt of phi b, which is equal to minus d by dt of integral B dot dA, and finally integral B dot dL is equal to mu 0 I plus mu 0 epsilon 0 integral epsilon 0 d by dt of integral E dot dA. The 4 equations in form of integrals, and these are the 4 Maxwell's equations. This is nothing but Gauss's law we have used right in the beginning. This tells me that the flux of electric field must be equal to the charge enclosed by epsilon 0. So, let me draw a figure here. So, if you take a surface like this, then the electric flux which is coming out of this, these are the E fields, this is integral E dot dA is equal to charge enclosed by epsilon 0. So, it says is that the first equation says that the net electric flux coming out from a closed surface, this integral with a closed surface must be equal to the charge enclosed divided by epsilon 0. So, depending on the sign of the charge, the electric flux is pointing away from this surface or towards the surface. So, the charge is positive, then we know the electric flux is coming out. If charge is negative, the electric field lines are entering the volume, entering the surface area. Also note that as we have discussed before, if the net charge inside is 0, the flux is 0, and that does not imply the charges are 0. I could have electric fields with net flux being 0. The second equation, which is in magnetic field, if I take another surface here, then I find that integral B dot dL, B dot dA must be equal to 0. No net flux coming out, because magnetic field lines are closed lines. As many field lines enter the volume as are coming out. So, magnetic field lines are closed lines, and so it also implies that there are no magnetic charges. That means, no points from which magnetic field lines emerge or get converged in. In other words, we say that magnetic monopoles do not exist, and so magnetic field lines, as we have seen before, are always closed lines, and so if you take a closed surface, the net magnetic flux through that surface will be 0. So, this is the second law which we have written. The third law, which is Faraday's law. So, if you take a loop, and if you have magnetic field lines crossing that loop, then this equation says integral E dot dL is equal to minus d phi b by dt. That means, a changing magnetic flux through this loop will induce an EMF in the loop, or a changing magnetic field will induce an electric field, and the direction of the induced EMF is decided by Lenz's law because of the negative sign. The induced EMF is always to oppose the changes in flux, that is Faraday's law of induction. And finally, we had the fourth equation, which was essentially, if I draw another figure here, and I had electric field lines crossing this, integral B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d by dt of phi e. So, magnetic fields get induced either by currents. So, that means currents can generate magnetic fields, or changing electric flux can also generate magnetic fields. This is the displacement current which we have discussed before. This term is the displacement current, which was introduced by Maxwell, and is a very important modification of Ampere's law. Remember, we had initially discussed this part, which was Ampere's law to calculate the magnetic fields produced by currents, and what he showed was that to be consistent you have to have another term in this equation which we call as the displacement current. So, these four laws of Maxwell's equations describe all electromagnetism, and they are a beautiful representation of the electrical and magnetic properties of the fields, the materials, etc. Now, in free space, if I look at a free space, for example, when there are no charges and no currents, these equations become the following. In free space, these equations become integral E dot dA is equal to 0, integral B dot dA is equal to 0, integral E dot dl is equal to minus d by dt of integral B dot dA, and integral B dot dl will be equal to mu 0 epsilon 0 d by dt of integral E dot dA. So, these equations only contain electric and magnetic fields. In free space, in the absence of any charges or in the absence of currents, flowing charges, I have these four equations, and these four equations, actually if you look at these two equations, they couple electric and magnetic fields. This electric field depends on magnetic field and magnetic field depends on electric field. So, these two equations actually couple the electric and magnetic fields, and this is what, as we will see later on, results in the existence of new forms of waves which are called electromagnetic waves. So, these are the four Maxwell's equations in what are called as integral form. In an advanced course, when you in your career, when you go into an advanced course, you will see that these equations can be converted into differential equations, and they form the four fundamental equations of electromagnetism. So, what Maxwell did was to generalize Ampere's law and introduce the displacement current to be consistent, and from here he actually derived a wave equation, an equation which describes the existence of waves, and he found that those waves which are waves of electric and magnetic fields have a certain velocity, and the velocity of those waves was approximately 3 into 10 to the power 8 meter per second. So, this velocity which he calculated was so close to the measured velocity of light at that time that he propounded, he boldly suggested that light waves are electromagnetic waves. Till that time, light waves were not considered to be electromagnetic, but he showed that from these equations you can predict the existence of waves which are called electromagnetic waves, and the velocity of those electromagnetic waves we found out depend on epsilon 0 and mu 0, and that velocity comes out to be so close to the known value of velocity of light at that time that he propounded that light must be an electromagnetic wave. and this was in 1865, and in 1888 Heinrich Hertz in Germany did experiments to generate electromagnetic waves of much lower frequency, and he showed that electromagnetic waves do exist, and the experiments conducted by Hertz were a dramatic confirmation of the predictions of Maxwell's electromagnetic theory. And today we find electromagnetic waves all around us, and we will, as we will go through a little bit of discussion of these electromagnetic waves, we will start to understand the importance of these electromagnetic waves and our basic understanding of the physics behind the description of electromagnetic waves. Now, before I move on to electromagnetic waves, you have done in class 11 discussed about waves, waves on a string for example, or acoustic waves, sound waves. So, I would like to recall some of the discussions you must have had in class 11 on waves before we move on to discussing electromagnetic waves. So, let us look at waves, waves on a string. Now, if you take a string, a long string, and if you take a string and pull it up like this and leave it, then you will develop a wave. For example, you can have a wave at this time. A little later what you will find is this disturbance moves here, and a little later this disturbance moves here, and a little later this disturbance. So, this disturbance is moving like this, and that represents a wave. So, what you have done is you have taken a string and pulled it up and taken it up and lowered it, generating a disturbance, and that disturbance moves in this direction with a certain speed called the speed of the wave, and this is a wave on a string. So, what is happening is the wave has been generated by moving the string up and down, and in that process you have given energy to the string, and that energy is propagating as a wave along the string in this direction. So, there are two things. One is the string is moving up and down with a certain velocity and energy, the wave is moving to the right with a certain different velocity. Now, this is one type of wave. I can generate different types of waves, but the most important are the sinusoidal waves. So, these waves are something like this. For example, this could be a function of x, this is y. So, I have a string which is along the x axis, and I take the end of the string and move it up and down periodically. So, I move the string up and down periodically, and in that process generate what are called as sinusoidal waves. I can describe the sinusoidal waves by the following equation. The displacement of the string at any value of x and time is given by a sin k x minus omega t. Now, I am sure you have discussed this in your earlier class, that the displacement of the string from the equilibrium position, this is the equilibrium position of the string. So, the string is moved up and down periodically, and in that process I generate waves on the string which are sinusoidal waves, because the dependence on time and space is a sine function. These are sinusoidal waves, and A is called the amplitude of the wave, A is called the amplitude of the wave, the maximum displacement, and this quantity k x minus omega t is called the phase. K x minus omega t is referred to as the phase of the wave, and so this is, let me explain what I have drawn is this shape of a string at some instant of time, say t is equal to 0. So, this represents a sinusoidal wave of amplitude a and described by a sin k x minus omega t. So, this gives me the displacement of the string from the equilibrium position as a function of space and time. So, let me try to draw two pictures here. One is I look at this wave at a given instant of time like here. Let me redraw the figure here. So, the general wave is described by y of x t is equal to a sin k x minus omega t. So, at t is equal to 0, some arbitrary time which I call t is equal to 0, y of x at t is equal to 0 will be a sin kx. So, what I have done is I take a snapshot of the string at a time which I call t is equal to 0. I take a snapshot, and that snapshot of the string, displacement of the string from the equilibrium position is given by a sin kx. So, let me draw the figure again here. So, a sin kx will look something like this. So, this is the amplitude a. Look here, the sine function varies between +1 and -1. So, it goes from plus a to minus a. So, this is y as a function of x. It is a sinusoidal function and which repeats after every this distance. This distance is referred to as wavelength. Wavelength of the wave. So, please remember this is a snapshot of the string at t is equal to 0. If I had a very fast camera, I could have taken a very short exposure of the string at some instant of time which I call t is equal to 0, and I will see an image of the string like this. This is the amplitude and this is the wavelength. So, you can see here the sine function at this point x was 0. So, the amplitude is 0. As x increases, the amplitude increases like a sine function. Then after this distance, the sine function repeats itself. So, in going from here to here, the quantity kx phase must have varied by 2 pi, because the sine function repeats itself whenever the angle changes by 2 pi. So, this distance must be such that kx must be equal to 2 pi. So, let me, if I call this distance as lambda, I must have k lambda is equal to 2 pi or k is equal to 2 pi by lambda. And this quantity k is called the wave number, or propagation constant. So, this describes, it is related to wavelength through k is equal to 2 pi by lambda, and it defines that how much is the distance over which the period of wave along the distance direction. So, after every distance lambda, the wave repeats itself. So, the distance from this point to this point is lambda, the distance from this point to this point is lambda, the distance between these 2 points is lambda. So, whenever you take 2 points of equal phase, the distance between them at a given instant of time is given by the wavelength of the wave. So, that is the wavelength. Now, let me look at another picture. What will the string look like from one given point? So, let me look at x is equal to 0. So, I position myself at some point which I call x is equal to 0, and so this is I position at this point on the string and look at this how the string varies as a function of time. So, y, let me recall, y of x t we have written as a sin k x minus omega t. So, at x is equal to 0, we have y of 0 t is equal to minus a sin omega t. So, if I position myself at a point which I call x is equal to 0, the amplitude of the string depends on time of the form minus a sin omega t. So, if I plot this function again, this is y as a function of now time at x is equal to 0, goes like this. This is minus a sin omega t. So, this is a here and that is minus a. And so, as you can see here, the string moves up and down and repeats itself after a certain time which I call t, capital T, the time period. So, the string goes up and down at a given instant at any point on the string and repeats itself after every time capital T. So, capital T must be such that the quantity omega t changes by 2 pi in going over a time capital T. At this point t was 0, at this point t must be such that omega t must have become equal to 2 pi. So, I can write omega times t is equal to 2 pi or omega is equal to 2 pi by t. And if I call the frequency nu is equal to 1 by t, this becomes omega is equal to 2 pi nu. So, omega is called the angular frequency, and nu is called the frequency. So, omega is equal to 2 pi nu. So, this quantity omega which appears in this equation is nothing but 2 pi times the frequency, and k which appears here is nothing but 2 pi by wavelength. So, I can write this equation in a containing wavelength and frequency. So, let me write y is equal to y of x t is equal to a sin, now k x is 2 pi by lambda x minus 2 pi nu t, that is omega t. So, this I can write as a sin 2 pi into x pi lambda minus nu t. So, this is the equation in terms of wavelength and frequency. Otherwise, the equation can also be written, this is same as the equation as this, a sin k x minus omega. These two are the same equations. This is written in terms of wave number and angular frequency, this is written in terms of wavelength and frequency. So, please differentiate between these two figures, one showing the shape of the string at a given time as a function of x. This is a snapshot of the string at any instant of time, the shape of the string how it will look at a given instant of time, and this other figure which is how the string at any point moves. That means, I position myself at a point on the string and see how that point on the string moves up and down as a function of time, and that is as a function of time here, this is a function of space coordinate here. So, we must be very careful in analyzing these two figures. One is a shape of the displacement of the string as a function of position, the other is a displacement of the string as a function of time. So, these two are important aspects. Now, I want to show you that this is a propagating wave, that this wave is propagating. So, my equation is y of x t is equal to a sin k x minus omega t. So, I want to draw how the string will look at a certain instant of time, say t is equal to 0, and a slightly later instant of time. So, let me draw how the, so at t is equal to 0, y of x t will be a sin k x, which we have drawn before. So, this is a function of x. So, it looks like this. So, this is at t is equal to 0. Now, slightly later time, say at t is equal to t 1, y of x t will be a sin k x minus omega t 1. So, slightly later time t 1, I look at the string y of x t is a sin k x minus omega t 1. This was at t is equal to 0. So, I had sin k x, this is at t is equal to t 1. So, I have sin k x minus omega t 1. Now, this is the same sine function as this, except that it is displaced. So, this argument was 0 at x is equal to 0, this argument will be 0 at x is equal to omega t 1 by k. So, what will happen is the string will now look something like this. So, this is at t is equal to t 1. Please note that at x is equal to 0, now it is minus a sin omega t 1. So, that is a negative displacement and the function becomes 0. So, this point has moved to this point, and this point now, where is this point? This point will be, so suppose I call this x naught x 1. So, this point x 1 is such that k x 1 minus omega t 1 is equal to 0. At this point, the argument of the sine function was 0, k x is equal to 0. At this point, k x 1 minus omega t 1 is again 0, the same point has moved here, and so x 1 and t 1 are related. So, x 1 k x 1 must be equal to omega t 1. or x1 by t1 is equal to omega by k. Now, what is x1 by t1? What we see is the wave which was at this point was here at t is equal to 0 has moved to this point in a time t1. Every point on the string, if you look at any point on the string, it has moved by a certain distance in a time t1, and so this must represent the velocity or speed of the wave. So, velocity of the wave is equal to omega by k. Omega by k is the velocity of the wave. So, that means in this equation, one is that it represents a wave, a propagating wave, as you can see here. A little later, for example, if I were to draw the same figure, a little later it will go like this. So, this is moving this side, it is moving like this. The entire wave is moving in the positive x direction. So, at t is equal to 0, t is equal to t1, t is equal to t2, and so on. So, as time progresses, the entire wave seems to be moving like this. So, it represents a propagating wave, and the velocity of propagation is omega by k. So, I can actually represent this in terms of 2 pi nu, omega was 2 pi nu and k is 2 pi by lambda, which is equal to nu lambda. So, this is the equation which you must have derived, velocity is equal to nu lambda. Velocity is related to the frequency and wavelength of the wave by v is equal to nu lambda. So, what we see is this particular form of an equation represents a wave, a propagating wave, propagating along the x direction, because at t is equal to 0 the wave was in certain position. At a slightly later time the wave has moved in the forward direction towards positive x direction, and so this represents a propagating wave propagating along the plus x direction. Now, I will leave it to you to discuss that a wave represented by y of x t is equal to a sin k x plus omega t represents a wave going in minus x direction. So, if this is a wave going in the plus x direction, I would like you to argue like I have done, that this is a wave which is going in this direction. So, depending on the sign between the space dependence and the time dependence part, the wave is represented, the wave is either going in the plus x direction or minus x direction, and that is a wave which is going in the negative x direction. So, please have a argument and try to plot figures and to show that this is a wave going in the minus x direction. So, what we have seen is this is a nice representation of a propagating wave, and this wave is what is this wave after all? This wave is nothing but how the string goes up and down as a function of time. So, there is a string which is going up and down, and that disturbance on the string is actually propagating in one direction, either the plus x direction or the minus x direction. So, that is a sinusoidal wave, and sinusoidal waves are very important waves, because later on in your studies you will see that any form of wave can be represented as a sum of different sinusoidal waves. This is a very important concept in physics, that you can represent any wave as a superposition of different sinusoidal waves of different frequencies, and this, so study of sinusoidal waves is very important from the point of view of physics. Also note some interesting aspect here. So, let me draw the string again, y as a function of x. Now, if you see here, the string is moving like this. So, a little later, as we draw before, it moved into this position. So, the string which was, for example, at this point the string which was here has moved here up like this, and as you can see here, the maximum extension of the string is also here. The equilibrium position of the string was like this. Now, it is stretched in this direction. So, maximum stretching is taking place here, and the point is also moving up and down at the greatest velocity at this point. So, in propagating waves, the potential energy of the string is contained in the extension of the string, in the tension which is extending the string, and the kinetic energy is determined by the energy of motion of the string up and down. And as you can see here, the point where the kinetic energy is maximum is also the point where the potential energy is maximum. So, maximum stretching appears here at the point of intersection with the axis here, and that is also the point where the velocity of the string is maximum in the upward or downward direction. So, for example, you can calculate for the velocity, you can calculate dy by dt, which is equal to. So, let me draw in this in a separate slide here. So, let me take a wave in the plus x direction, y is equal to y of x t a sine k x minus omega t. So, if you calculate the velocity of the string is actually given by dy by dt, which is minus a omega cos k x minus omega t. Y is the displacement of the string. How does the displacement of the string vary with time, and how does the stretching of the string vary with position? That means, how does y depend on x, that is stretching, and that is given by a times k times cos k x minus omega. And as you can see here, both of them are described by the same cosine function. Points where the velocity is maximum, where the cosine function is 1, is also the point where dy by dx is maximum, where the cosine function is 1. This determines the kinetic energy of the string, that determines the potential energy of the string, and they are in phase. So, you find that in propagating waves, the potential energy and kinetic energy are both in phase, and as the wave propagates, it carries this energy. So, this was a very brief description of waves that you must have studied in class 11. I would urge you to go back and pick up the class 11 book and see for yourself different properties of waves that you must have discussed at that time. You must have discussed, for example, waves in gas, sound waves in a gas, for example. You may have discussed superposition of waves and so on. So, I would urge you to go back and refresh your memory as far as the waves are concerned, because now we will be discussing a very important class of waves called electromagnetic waves. Now, electromagnetic waves are quite different from the waves that you must have discussed till now. Waves on a string, for example, you must have seen waves on a water surface. So, in a string, what happens is the string is moving up and down, and in that process there is a wave which is moving. So, the string is not moving in the forward direction, string is only moving up and down, and the wave is going in a certain direction. Now, remember, these are called transverse waves because the string moves up and down in the vertical direction, while the wave moves in the horizontal direction. The direction of propagation of the wave is perpendicular to the direction of motion of the string, and so this is the transverse wave. So, I could have the string moving up and down and the wave propagating like this, or I could have the string going forward and backward and the wave propagating like this. So, these are two different types of transverse waves, one which is displaced along the y direction and propagating along x, the other is displacement along z direction and propagating along x. So, you can have two different transverse waves. Sound waves represent what are called as longitudinal waves, where there are compressions and rarefactions which are propagating in the wave. So, when I speak, I am generating sound waves. So, there are waves of compressions and rarefactions in the air which is surrounding me here, and those compressions and rarefactions are such that air molecules are. So, for example, when I speak, the air molecules are moving like this, and the sound wave is propagating in the forward direction. So, these are called longitudinal waves. The displacement of the particle is along the direction of motion of the wave. Now, electromagnetic waves are also transverse waves. Now, unlike in waves on a string, which requires a string for propagation of the wave, or sound waves where you need gas or some kind of a medium in which you have to propagate, electromagnetic waves can propagate in free space. Light is a form of electromagnetic wave, and we are getting light from the sun. we are getting light from stars which are millions of light years away. So, we are getting light from all around the place, and please remember there is hardly anything in between the outside the solar system and the solar system, between the stars and us, or between sun and us. So, these waves are able to propagate in free space, and so they are a completely different type of wave. They do not need a medium to propagate. Of course, the presence of a medium can change their propagation properties, but you do not need a medium to propagate. And so, these electromagnetic waves are characterized by electric variation of electric and magnetic fields in space. So, these are the waves which are electromagnetic waves are waves in electric and magnetic fields. They are represented by electric and magnetic fields and not displacement of a string or pressure in a gas. They do not need a medium, and they are actually nothing but electric and magnetic fields which are propagating in space, carrying energy and momentum. So, before we discuss more details, what I would like to do is to draw a figure to show you how electromagnetic waves are represented, and describe a bit about the figure, so that you understand very clearly what is the meaning of the figure that we plot. Okay, so, couple of things which I need to mention before I plot the figure. The electric and magnetic fields are perpendicular to the propagation direction. That is why they are called transverse waves. The electric and magnetic fields of the wave are perpendicular to the propagation direction. Electric field is perpendicular to the magnetic field, and this vector E cross B is along the direction of travel of the wave. So, electric and magnetic fields are perpendicular to the propagation direction. Electric and magnetic fields are perpendicular to the propagation direction. Electric field is perpendicular to the magnetic field, and electric field cross magnetic field is along the propagation direction. So, that means electric field, magnetic field and propagation direction form a right-handed coordinate system, and also electric field and magnetic field are in phase. So, the electric field and the magnetic field are always in phase in these propagating waves, just like I showed you in the string. The kinetic energy and the potential energy are in phase in the propagating wave. Here the electric and magnetic fields are in phase. So, let me draw a figure which represents an electromagnetic wave, and then try to describe to you what is the meaning of that. Okay, so let me draw the electric field. So, this is the electric field, and let me draw the magnetic field, which will look like this. So, let me draw some vectors here. So, these are the way I represent electric fields. Magnetic fields are perpendicular So, please note that, so if I call this x, y, z, so this is the electric field and this is the magnetic field. And that is so, please note this figure. What I have drawn is how does the electric field vary with position. This is at some instant of time. Remember, just like I drew for these waves on a string, I take some instant of time which I call t is equal to 0 and plot how the electric field varies with position and how the magnetic field varies with position. So, you can see here, first thing is the electric field, the wave is actually propagating along the z direction. It is a wave propagating along the z direction, we will discuss that, and the electric field is perpendicular to the propagation direction, the magnetic field is perpendicular to the propagation direction. So, the wave is a transverse electromagnetic wave. It is a transverse wave because electric fields and magnetic fields are perpendicular to the propagation direction. Second, the electric field and magnetic field are perpendicular to each other. So, electric field is perpendicular to magnetic field at every point. Here everywhere electric field and magnetic field are perpendicular to each other, and electric field. So, electric field is pointing along x direction, in this figure magnetic field is pointing along y direction. So, E cross B, which is x cap I cap cross j cap, has to be k cap, and so the wave is propagating along z direction. So, electric field, magnetic field and the propagation direction form a right handed coordinate system, x, y, z, electric field, magnetic field, propagation direction. Okay, now, one has to be a little careful in sort of trying to figure out this figure, because it is a very abstract figure in the following sense. Please note that these arrows only represent the magnitude and direction of the electric and magnetic fields at every point on the axis of this wave. So, this arrow implies that the electric field at this point has a large magnitude and is pointing in the upward direction. At this point, the electric field at this magnitude and pointing in downward direction. At this point, the magnetic field is along the y direction and has this magnitude. So, all these fields are actually fields at various points along the axis, and these are the magnitude and direction of the electric and magnetic fields. Please remember that these arrows only represent the magnitude and direction of the fields and do not represent any displacement of any object. In the case of the vibrations of a string, waves on a string, the y versus x was actually a plot of displacement of the string as a function of position at different points. So, the position of the string was being marked there. Here in this figure, there is no displacement, there is nothing connecting these 2 points. This arrow represents the fact that at this point the electric field has this magnitude and direction, at the same point the magnetic field has so much magnitude and direction. Similarly, here the electric field has so much magnitude and direction, this magnetic field has so much magnitude and direction. So, these are all nothing but electric and magnetic fields represented along the axis, but by these arrows, and they do not, this line does not represent a displacement of a particle or a displacement of a medium or anything. So, this one must be very, very careful, and this, whenever you look at a figure of electromagnetic waves, please keep this in mind, that unlike the case of vibrations of a string, there is nothing which is displacing up and down. All that it implies is, as the wave propagates, for example, like this, at this point, if the electric field is, if the wave is propagating like this, if the electric field is pointing up, magnetic field is pointing here, and at this point, if the electric field has a certain magnitude, there is a certain magnitude of magnetic field. At a little later time, maybe the electric field is pointing down and the magnetic field is pointing in another direction. So, you have essentially the electric and magnetic fields at this point will vary with time. So, for example, the electric field will start from 0, increase in magnitude in the upward direction, and then again become 0 and increase as a negative direction at this point and oscillate with time. for a sinusoidal electromagnetic wave, which I will write down in the equation, at every point the electric field and magnetic fields will vary sinusoidally with time. So, if I look at a point, if I position myself at a point and if I had a detector for electric field, that detector will tell me that as a function of time the electric field is varying. It starts from some value, keeps on increasing to a maximum, then becomes 0, then starts to increase in the negative direction, becomes a maximum, becomes 0 again, and periodically oscillates like simple harmonic motion. But there is nothing moving, it is simply the magnitude and direction of electric fields. Similarly, at the same point, when the electric field is increasing, magnetic field is also increasing, but in the perpendicular direction. So, if the electric field is pointing up, the magnetic field is pointing towards me, so that E cross B is in the direction of motion. If the electric field is pointing up and magnetic field is pointing towards you, the direction of propagation must be here. So, please remember, electric and magnetic fields are perpendicular to propagation direction, electric and magnetic fields are both perpendicular to each other, electric field cross magnetic field vectors must be along the propagation direction. And this figure is a very important figure that you will find in your textbook and at every place. This is a figure which represents, this is a bit of abstract figure. This line does not represent any motion of or displacement of any object. All it says is it is a point connecting the tips of the electric vector as a function of position here, and the tips of the magnetic vectors as a function of position. So, at this point, when the electric field has this magnitude, magnetic field has this magnitude, at this point if the electric field has this magnitude, magnetic field has this magnitude. So, keep this in mind when you are looking at this figure like this, and this is a very important aspect that we must remember when we are looking at such figures. Now, let me write down an equation. Now, in principle we could use those Maxwell's equations and derive an equation which predicts the existence of these waves, but that is beyond the scope of this course here. So, what I will do is I will write down the solution of those equations in the form of an electromagnetic wave and show you that those equations are consistent with the Maxwell's equations that we have written earlier. So, I will write the solutions and show you that those solutions are representing waves which we call as electromagnetic waves, and those solutions are consistent with the Maxwell's equations we wrote earlier. So, let me write down electromagnetic waves. So, sinusoidal waves, and these are electromagnetic waves again. So, let me draw the figure again here. So, I had x, y and z. So, I had drawn the electric field wave like this and magnetic field waves. So, magnetic field is in this plane, the electric field is in this plane. So, I will write, for example, E is equal to I cap E 0 sin k z minus omega t, and B vector is equal to j cap B naught sin So, these are equations which are very similar to the equations we had written for waves on a string. We have to write for electromagnetic waves, we have to write an equation for the electric field as a function of position and time, and the magnetic field as a function of position and time. This is a wave propagating along the z direction. Please remember, in the case of the waves on a string, I had written it as kx minus omega t, which represented waves along the x direction. Here I am writing kz minus omega t, that means this is a wave propagating in this direction, in the plus z direction. These are sinusoidal waves because they are sine functions. As you can see, both are in phase because both are sin kz minus omega t. Their directions are such that if E is along I cap, B is along j cap. So, E and B are perpendicular to each other, and both of them are perpendicular to the propagation direction, which is along z cap direction. Wave is propagating along z, electric field is along. So, electric field is along this direction, this is the electric field direction, and this is the magnetic field direction here. So, magnetic field seems to be in the magnetic field is in the yz plane, the electric field is in the xz plane. They are in phase, they are perpendicular to each other, and E cross B is nothing but I cross j, which is along k cap direction, which is the propagation direction. So, as before, k is equal to 2 pi by lambda, lambda is called the wavelength of the electromagnetic wave, and omega is equal to 2 pi nu, nu is called the frequency of the electromagnetic wave. So, in this k is 2 pi by lambda, lambda is the wavelength of the electromagnetic wave, omega is 2 pi nu, nu is the frequency of the electromagnetic wave, k is called the propagation constant or wave number, and omega is called the angular frequency of the electromagnetic wave. So, the electromagnetic waves are now described by these, and these are one type of solutions of electromagnetic waves. These are called sinusoidal waves, and this represents one type of wave. Now, here as we have discussed before, this quantity, the velocity of the wave, is equal to omega by k. This ratio omega by k represents the velocity of the wave, and these two represent sinusoidal waves, electromagnetic waves. The first equation represents the electric field variation with position, and the second equation represents magnetic field variation with position. Now, I want to before we discuss these waves in more general, I would like you to show a figure, a slide, which shows you the type of electromagnetic waves at various frequencies and various wavelengths. So, this is the electromagnetic spectrum, this is the spectrum here. In this direction the frequencies are increasing, which means a decreasing wavelength here. As you can see, frequency and wavelength are inversely related to each other. The velocity is a product of frequency and wavelength. So, as the frequency increases from left to right in this figure, the wavelength decreases. So, you can have waves of different frequencies and different wavelengths here. So, there are starting from very low frequencies, electromagnetic waves can occupy where frequencies of very high values. So, we have given different names for waves of different frequencies. Here you have what are called as radio waves with frequencies of the order of a megahertz, 10 to the power 6 hertz. Then you have microwaves with frequencies of the order of a gigahertz, 10 to the power 9 hertz. Then you have an infrared region here, which has wavelength, which is frequency slightly less than visible, and this is the visible region of the electromagnetic spectrum. So, this is the complete electromagnetic spectrum. The visible wavelengths are here, and the frequencies range from about 4 10 to the power 14 hertz to 7.5 10 to the power 14 hertz, and then comes ultraviolet in this region about 10 to the power 16 hertz frequencies. Then we have X rays, which are 10 to the power 18 hertz frequency, and then we have gamma rays, which are 10 to the power 20 hertz frequencies. So, you can have electromagnetic waves of varying frequencies, and the visible spectrum to which our eyes are sensitive forms a very small fraction of the entire electromagnetic spectrum. So, this is as the frequency increases here, the wavelength drops down, and you can actually calculate and show the wavelength of these waves are much shorter than the wavelength of these waves, and I will leave it to you to calculate the corresponding wavelengths knowing the speed of these waves, because we will now in the next class what we will do is discuss in more detail, starting from this equation which I wrote down of the electromagnetic waves, electric and magnetic fields. I will show you that these two equations are consistent with the Maxwell's equations, and I will show you that omega by k, which is the velocity of these waves, is related to epsilon 0 and mu 0, the dielectric permittivity of free space, and dielectric permeability of free space epsilon 0 and mu 0, and that is where Maxwell connected electricity and magnetism and optics. He showed that optical waves must be electromagnetic waves, because he found out that the speed of these waves is so close to the speed of light waves that light must be an electromagnetic wave. So, I will stop my class here right now, and we will continue with our discussions starting from these two equations, and I will show you, we will calculate the relation between electric and magnetic fields here, and I will show you that the velocity of the waves of these waves is nothing but the velocity of light in free space. Thank you very much.